Okay, in this lecture, we're going to be going over goodness of fit hypothesis testing. So you use goodness of fit hypothesis testing to compare an observed frequency distribution to an expected frequency distribution. So what does that mean? If you recall back to um, when we were doing probability, we would have a frequency distribution. We actually had frequency distributions all the way up in Unit 1. And so you have frequency distributions, essentially, you have categories, and you have how often an observation occurs in each one of those categories or groups. So, for instance, let's take an example. Um, Bubba's Fish and Pasta is a chain of restaurants along the Gulf Coast of Florida. Bubba is considering adding steak to the menu. Before doing so, he hires a research firm to conduct a survey to find out what the patron's favorite meal is when eating out. Here are the results of the survey of 120 adults. So you have 120 adults that were surveyed. Right here is the column of observed results. Right here is the column of what you expected to occur. So the research question is the difference in the number of times each entree is selected due to chance, or should we conclude that the entrees are not equally preferred? So what this is really asking is the difference of, 24 to 30, 32 to 30, 35 to 30, 29 to 30, is that completely due to chance? Or is that different enough? Is the observed frequencies, is it different enough from the expected frequencies to say that it actually is different? Okay? That the observed is actually different from what was expected, or was it just completely by chance? So, in order to do this, the first thing that you do, you can do this by hand, and it's really easy to do it by hand, or you can do it with the computer program. This right here, this is with the computer program. I put it into Excel, and I'm going to show you how easy this is. Okay, so let's see, Control C. So then I go to Data, Megastat, and then I go to chi-squared, and I click on Goodness of Fit Test. So, actually, I've got to put expected 30, 30, 30, and 30. Okay, so chi-squared, goodness of fit test, and then I'm going to do the observed value. These are the observed values right here. And then I'm going to do the expected values, which is right here. And you notice they're paired up. I highlighted them in a row. Okay, and then I click OK, and it gives me the observed values, the expected values, and it gives me chi-squared is down here, the degrees of freedom is right here. I can zoom in a little bit. Degrees of freedom and the probability of randomly getting this result, given that the expected values are true. Okay, or the expected values really are what we should have expected. So in order to do that by computer, I showed you how to do that really quickly, but in order to do this by hand, it's also really simple. So you take the difference between the observed and the expected, which gives you 2, -6, 5, and -1. Okay, you and then you square all of those. And when you square all of those, it gives you, and then you square all of them and you divide it by the expected score. So you square it and it squaring it and dividing it by the expected score gives you 0.033. Squaring this, 25 divided by 30 is 0.833. 36 divided by 30 is 1.2. And then 4 divided by 30 is 0.133. You add all of those together, and this number right here is chi-squared. But if we go one further, you can see the chi-squared score for that category divided by the total chi-squared gives you 6.06. 1.2 divided by 2.2 gives you 54.55. Well, and then 0.833 divided by 2.2 gives you 0.3788, and then 0.033 divided by 2.2 gives you 1.52, and these right here are the percentages of that of this category. So this is chicken, fish, beef, and pasta. This is the percentage that observed score compared to that expected score contributes to the 2.2 in the chi-squared. So if you want to know which one of these, I'm sorry, I keep going back and forth. If you want to know which one of these categories contributes the most to the chi-squared result, that would be 54.55, which would be fish. So the goodness of fit test indicates, let's take a look at this. So first of all, what's the null and alternative hypothesis? Well, it's a little bit different this time. The null and alternative hypothesis, instead of them being written with symbols, we're writing them with words. Okay, so the null hypothesis says there is no difference in the proportion of adults selecting each entree. Another way that you could write this, because the null hypothesis is written pretty much exactly how the question is asking it. The restaurant owner wants to know, is there a difference between what individuals desire to eat? And so, it's written in that way, saying, there is no difference in what they want to eat. There's no difference in the proportion of adults selecting each entree. Another way that you could write this is actually, let's do h sub 0 and h sub 1. You could write this: there is no difference between the observed samples preference of entree and expected preference of entree. Okay. And then for the alternative hypothesis, you can pretty much do the exact same thing and do there is a difference. Okay, so in this particular situation, a lot of times when we're doing null and alternative hypothesis, the alternative hypothesis is what we actually expect to happen, and the null hypothesis is what we don't expect to happen. But here, a lot of times, the null hypothesis, we need to make sure that we realize that the null hypothesis, all that that's really saying is we don't think that there's going to be any difference. So there's not going to be any difference between the observed and the expected. Or another way that you could say it here, because all of the expected are the same, is we don't believe that there's going to be any difference in the proportion of the expected values of the entree categories. Okay, and let's do this. I'm just gonna, I don't know how to do the little accent mark, so that's why. There we go. So what is the level of significance? I didn't put it up here, so I just put 0.05. But what is, and the reason why I put 0.05 is because I'm okay with 0.05 or 5% chance in type 1 error. Okay, so what is the test statistic? The test statistic is chi-squared, and you notice the test statistic value is right here. That's t calculated, or sorry, chi-squared calculated. I don't know why I said t calculated. Okay, so what is the decision rule? The decision rule is to reject the null hypothesis if chi-squared is greater than 7.815. Okay, 7.815, and so you see the critical value right here, 7.815. So we are going to reject the null hypothesis if chi-squared calculated is greater than 7.815. So what is our decision? Based on the chi-squared value being 2.2, so you notice 2.2, and let's find where that is right here. Chi-squared value is 2.2. We fail to reject the null hypothesis because chi-squared calculated is less than chi-squared critical. And then you can see, once again, the value of the test statistic and the p-value, or the probability of this randomly occurring given that the null hypothesis is true. The probability of this result randomly occurring given that the null hypothesis is true is 0.5319 or 53.19%. So that p-value signifies the probability of getting this result or something more extreme than this. Okay, something more extreme than this would be anything that's 2.2 or greater. Okay, so how could we interpret this in a way that we would tell our boss? We could tell our boss there's no evidence of a difference of preference between the 4 meal choices. Steak would be just as well received as fish, pasta, or chicken. And so we don't have any evidence to say that they're different at all. We need to say that they're all the same. Another way that you could say this is there's no difference between what we observed and what we expected, or there's no difference between the individual's preferences that were measured and what we expected them to be. Because this is a goodness of fit test. Once again, is how well does the data that we collect fit with what we expected. In this case, we expected it all to be identical, so the goodness of fit is it was really close to it all being identical, because 2.2 chi-squared, we could have gotten that randomly, or something more extreme than that. There's a 53.19% chance that we got that just by chance. So that is chi-squared.